In this video, we are going to continue to look at some mole conversions practice problem. And we are going to start by looking at several problems that have two different substances. So where we are starting and ending in a different substance and therefore have to use a mole-to-mole ratio. This first problem says how many moles of oxygen are in 12 moles of silicon dioxide. So the first thing we want to do is plan our strategy. So we're starting out in moles of silicon dioxide. So I'm going to circle that on my mole chart here. And we are ending in moles, but when we end, we're ending in moles of a different substance. We're actually ending in moles of oxygen, even though we're starting out in moles of silicon dioxide. And so I'm going to start with moles of one substance, but I'm actually going to end with moles of a totally different substance, which means I do need to do dimensional analysis. I'll start by writing my given value, unit, and substance, so 12.0 moles, I'll abbreviate MOL. Silicon dioxide, I know is one silicon, di meaning two oxygens. And I always like to put my starting value over 1 to remind myself that everything is up in the numerator. Now, my mole-to-mole step, I'm going to drag and drop my moles of silicon dioxide to the bottom of my conversion factor. It's always easy to get the bottom of your conversion factor because you just drag and drop what you had on top previously. And I'm going to moles of my new substance. So notice that my unit here is not actually changing, but my substance is. So instead of moles of silicon dioxide, now I just have moles of oxygen. This is basically asking me to say, okay, if I have a silicon dioxide, every time I have that, I have one silicon and two oxygens. And that's basically what this question is asking us to do. For every mole of silicon dioxide, how many moles of oxygen do we get? So what's the ratio between those things? So for every one silicon dioxide, I get two oxygens. So I'm going to fill in those numbers. A 1 next to moles of silicon dioxide is 2 moles of oxygen. And up until now, you've probably been told to always put a 1 next to mole. And that is usually true. The one time when that is not the case is when we are doing this mole-to-mole step using a mole ratio. The number of moles in a mole ratio will not always be 1-to-1, and therefore you may put a different number next to moles in a mole-to-mole step, meaning you're not changing the unit, you're only changing the substance at hand. So that's exactly what we did here. For every 1 mole of SiO2, we have 2 moles of oxygen. So now we'll just solve this problem. 12 times 2 is 24, but I do need to keep 3 significant figures here, so I'll put 24.0. My unit is moles, and my substance is oxygen. So we'll just box our final answer there. This next problem, how many moles of oxygen are in 535 grams of aluminum carbonate? So we start out with grams of aluminum carbonate, and I'm going to write that out first, 535 grams, and I do need to know the formula for aluminum carbonate. And many of you might be tempted just to write aluminum and write CO3 and call it a day, but that's actually incorrect. We do need to crisscross to get this formula. Aluminum has a charge of +3 and carbonate has a charge of -2, meaning that our formula for aluminum carbonate is Al2CO3 with a 3 outside the parentheses, which, as you can tell, probably has a much different molar mass than AlCO3, which is what you would have written if you forgot to crisscross. I'm going to cross that out there to remind us not to do that. So 535 grams of Al2CO3, 3. So there's my given value, unit and substance. I'll put that over 1. And now I want to kind of plan my strategy to get to the end of this problem. So while we are starting in grams or mass of aluminum carbonate, we are ending in moles. Now, you might say that mass to mole is only one step, but in actuality, we're not ending in moles of aluminum carbonate, we're actually ending in moles of oxygen, which is a totally different substance. So we're not going to, right here, moles of the same thing, we're actually going to moles of a new thing on our chart, which is the orange over here. So that means that in our problem, we're actually going to need one conversion factor to get from grams to moles, and then another conversion factor to get from moles of our first substance to moles of our new substance. So two conversion factors. I'm going to go ahead and draw my two lines for my conversion factors. And it's okay if you don't do that first, it doesn't really matter. But I like to kind of plan my strategy ahead of time. I'm actually going to move this down just a tad so we have a little bit more room. Okay, I'll set up my units and substances first. So first I'll drag and drop my grams of aluminum carbonate to the bottom of my first conversion factor, Al2CO3, 3. And in my first step, I'm going to moles of the same thing. So grams to moles of Al2CO3, 3. First step's written out. So now for my second step is my mole to mole step. So I'll drag and drop moles of Al2CO3, 3 to the bottom. And it takes a little bit of time to write out these formulas, but it is important to have value, unit, and substance everywhere. And this time I'm going to moles of my new substance. So my unit is actually not changing. I'm still in moles, but instead of moles of aluminum carbonate, now I'm in moles of oxygen. So let's fill in some numbers. So we know that anytime we're converting from moles to some other unit, we're going to put a 1 next to moles. So I'm going to start by doing that. 1 mole of aluminum carbonate is going to equal some number of grams. But to get that, I need a periodic table, and I need to add up the molar mass of aluminum carbonate. So your molar mass might be slightly different depending on the number of significant figures shown on your periodic table. But I have 2 times the mass of aluminum, which is about 27 grams per mole. Then I have 3 carbons, so 3 times about 12. And then I also have 9 oxygens, which has a mass of about 16. So if I add all that up, and I'm going to do this in my calculator real quick. 2 times 27, so that gives me 54. 3 times 12 gives me 36. And 9 times 16 gives me 144. So then I'll add all those values together. 144 plus 36 plus 54 to give me 234 grams per mole. Now I did round to whole numbers here, and your teacher may have told you to round differently, so just pay careful attention to what the particular problem or what your teacher asks you to do. So 234 grams of aluminum carbonate in 1 mole of aluminum carbonate. Now that we have that molar mass in place, the last step is to figure out our mole to mole ratio. Now all we need to do here is look at our formula and kind of break it apart. So in every 1 mole of aluminum carbonate, I just need to read the subscripts to figure out how many oxygens there are. And I see that there's a 3 outside the parentheses and a 3 inside the parentheses. So 3 times 3 means that in every mole of aluminum carbonate there are going to be 9 oxygen atoms, or 9 moles of oxygen. If we're saying moles of aluminum carbonate, then we need moles of oxygen. If we have molecules of aluminum carbonate, or formula units, or particles, then it would be an atom of 9 atoms of oxygen. So we're just looking at the ratio here. So now that we have this entire problem set up, we just need to multiply and divide in our calculator. So 535 divided by 234 times 9. When I do all of that math, I got the number of 20.576. Somewhere around there. But of course I do need to round to correct sig figs, and looking back at my problem, 535 only has 3 significant figures. So I'm going to underline the numbers I'm keeping, and then I'm going to look at that 7 to determine whether I should round up or stay at a 5. And of course here I'm going to round up to 20.6 moles of oxygen. And I'll just box in my final answer. And there you go. This next problem asks us to find how many grams of oxygen are in 9 moles of aluminum carbonate. So the first thing that we need to do is figure out the formula for aluminum carbonate. That way we can write our given value, unit, and substance. So 9.0 moles, and aluminum carbonate's formula might actually be the same one that we used in the previous problem. So we can look back at our previous problem. Aluminum carbonate is Al2CO33. We've already crisscrossed it once. Al2CO33. It is important that you have the correct substance written down though, so double check those things. Now, we are going from moles of aluminum carbonate, so we're starting with moles, and we are going to grams, but instead of going to grams of the same substance, we're actually going to grams of oxygen, which is a different substance than where we're starting. So we'll go over here to grams on the other side of our chart. This means we'll need 2 steps. Our first step is actually going to be our mole to mole step, and then our second step will take us from moles of oxygen out to grams of oxygen. So our first step, we will drag and drop our moles of Al2CO3 from the top to the bottom. Al2CO3, 3. And we are going to moles of our new substance, which in this case is oxygen. Now, for every 1 mole of Al2CO33, we're actually going to have 9 moles of oxygen. So we'll put that up at the top. It's a 1:9 ratio here, or 9:1 ratio. And then our second step, since we did our mole to mole step, now we need to go from moles out to grams. So we'll start by drag and dropping moles of oxygen to the bottom, and on top we'll put grams of oxygen. Now we already filled in the numbers for our mole to mole step, but any time that we are not in a mole to mole ratio, we always are going to put a 1 next to moles. So I'm going to put my 1 mole of oxygen on bottom, and then to figure out how many grams of oxygen are equivalent to a mole, I'm just going to look at a periodic table. And oxygen's molar mass is 15.999 grams, so I'm going to round that to 16 grams. Now to get our final answer, we'll just multiply and divide here. So 9 times 9 is 81, times 16 is 1,296. Now, given in our problem, we only have 2 significant figures, so we do need to round our final answer to just 2 sig figs. So I get to keep these first 2 digits, and I'm going to look at the next digit to determine if my 2 will stay a 2 or round up. In this case, it's definitely going to round up to a 3, but 13 is nowhere near 1,296, so I also need to add 2 zeros at the end to hold the place value of the number. So 1,300 grams of oxygen, and this time I'm actually going to write out the word oxygen since I have zeros at the end of my answer, so that way my chemical symbol is not going to get confused with part of my value here. So 1,300 grams of oxygen is the final answer. On 22, we are asked how many atoms of gallium are in 67.0 grams of gallium sulfite. So we are starting with 67 grams of gallium sulfite, so I'll circle mass or grams on my chart, and we are going to atoms of gallium, so a different substance here. So when I circle my particles, which I know an atom is a type of particle, I'm circling it on the other side of my mole conversions chart. This means we're going to need 3 steps. Our first step will take us from grams of gallium sulfite to moles of gallium sulfite. Our second step will take us from moles of gallium sulfite to moles of just gallium, and our third step will take us from moles of gallium out to atoms of gallium. So 3 steps here. So we're starting out, I'll write 67.0 grams of gallium sulfite, and to get that formula I am going to need to crisscross. So gallium has a +3 charge. Sulfite is SO3 with a -2 charge. So when I crisscross, I get Ga2, SO3, 3. So Ga2, SO3, 3. I like to put this over 1. And then I know I'm going to need 3 conversion factors. And I know I'm going to run out of room here. So I might actually have to put my answer up above a little bit. So when we write our answer, we'll just write it up here. So I'm first going to drag and drop grams of Ga2, SO3, 3. And I'm first going to take that into moles. So on top I'll put moles of Ga2, SO3, 3. So there's step 1. My next step is going to be my mole to mole step. So I'll use my mole ratio to fill that in. I'll put moles of Ga2, SO3, 3 on the bottom. And then I'll put moles of my new substance, which is just gallium, Ga, on top. And then in my final step, I'll take my moles of gallium, and I will take that into particles or atoms of gallium. Atoms of gallium. And remember, there's no abbreviation for particles or atoms or formula units or molecules. You just have to write out the whole word. So I'll start by filling in my non-mole ratio. Anytime I see mole in a step that's not a mole to mole step, I'm going to put a 1 next to mole. So I'll do that here on top of my first conversion factor and on the bottom of my last conversion factor. I already know the number of atoms in a mole. That's Avogadro's number, 6.022 times 10 to the 23rd. So I'll fill that one in. And then I do need to calculate out the molar mass of gallium sulfite to fill in the bottom of my conversion factor here. So I'm going to kind of add this up. I have 2 galliums, I have 3 sulfurs, and I have 9 oxygens in the formula. So gallium's molar mass is about 69.7. So 2 times 69.7 gives me 139.4 if you type that into a calculator. Sulfur's mass is 32.07. So 3 times that gives me 96.21. And then oxygen's molar mass is right about 16. So 9 times 16 gives me 144. So I'm going to add all these values up real quick, and that gives me 379.61 grams per mole. So that number is what I'll fill into the bottom of my conversion factor, 379.61. And then the last thing I need to do is fill in my mole ratio, and I know for every 1 gallium sulfite, I end up with 2 galliums. So I'm going to fill in a 1 next to moles of gallium sulfite and a 2 next to moles of gallium. Now that I have all my numbers in place, all that's left is to type this into a calculator. So 67 divided by 379.61. And I'm going to type this in with you. 67 divided by 379.61 times 2. And then times 6.022, I'm pushing my special button, e to the 23rd. So when I did this, I got a big long number, 2.1257, a whole bunch more decimal places appeared, but I know that I'm not going to need all those, so I'm just going to go ahead and round off, because I actually only need 3 significant figures. So I get to keep these first 3 digits and decide if I'm going to round up or down. And I am going to round up here, so 2.13 times 10 to the 23rd power. And my unit should be atoms, and my substance is gallium. So there is my final answer up here. Last but not least, we have how many atoms of hydrogen are in 56 liters of H2S gas. It already gave us the formula here, which is kind of nice. So we're starting out in liters of H2S, and we're going to atoms of just hydrogen, so a different substance, particles of a different substance. So we'll start out with 56 liters of H2S. It's nice that they gave us the formula this time. And then I see on my chart that I'm going to need 1, 2, 3 steps. So I'll go ahead and put in my conversion factors, or the lines to put my conversion factors on. On the bottom of my first conversion factor, I will simply drag and drop liters of H2S. And I'm first going to moles of H2S. My next conversion factor will be my mole to mole step. So we'll have moles of H2S on bottom. And still the same unit of moles on top, but this time it will be moles of hydrogen, my new substance. And then finally, we'll take our moles of hydrogen out to atoms of hydrogen. So I know that in my mole to mole step, I will need to figure out my ratio of H2S, how many H2S's to how many hydrogens. So in every one H2S molecule, I have 2 hydrogens. So I'll take this information and use this to fill in my mole to mole ratio. So 1 mole of H2S is equivalent to 2 moles of hydrogen. And then in my non-mole ratio steps, I know that I always put a 1 next to mole. So here 1 mole of hydrogen and then 1 mole of H2S. Now both of these I already know off the top of my head. 1 mole of any gas is equal to 22.4 liters. And it tells me that it is H2S gas. And then 1 mole of hydrogen is going to be equal to 6.022 times 10 to the 23rd atoms. That's Avogadro's number of atoms. So now I just need to multiply and divide. So let's do this in a calculator. 56 divided by 22.4 times 2, and then times Avogadro's number. So my final answer is 3.011 E24. Actually, I guess that's not my final answer because I do need to round to significant figures here. I only get 2 sig figs, so I'm going to keep the 3.0 part. And then I'm going to round down to 0 because that's a 1 that comes next. I can't keep that E, so I'm going to change it to real scientific notation, times 10 to the 24th power. And then I do need a unit and a substance, which I didn't really give myself enough room here, so I'm going to go ahead and just move this on over. So that way I have room to write atoms of hydrogen. So then I'll just box in that final answer. Kind of wound up with my line there as part of my box, kind of ending up there. So there is my final answer, 3.0 times 10 to the 24th atoms of hydrogen.